only accentuates electron delocalization. I mentioned this several times before. In charged systems, and delocalized systems that are charged, all the p orbitals, for example, that in the neutral may be slightly distorted and tilted and so forth, when the charge comes in, they all straighten up, because they want to line up perfectly for this charge to delocalize, the whole, as it were, whole delocalization over the entire pi frame. And this is true not only for plus charges, but also for minus charges or radicals. Okay, everything lines up because it wants to spread out these electrons in space as best it can. If you do meta attack, again, you're bypassing this X, and so you don't gain much. So while X deactivates slightly, electrophilic aromatic substitution in competition with benzene would lose out. It nevertheless does ortho-para substitution. So here's sort of a summary of substituent effects, and this is from your book, where you can see we separate things into moderate to strong activators, weak deactivators, and strong deactivators. And the strong ones are the amino and the alkoxy functions. And I've added here for your own calibration actually relative rates of nitration compared to benzene itself. And you can see the activation, it's about 10 to the 5 for amino. Okay? 10 to the 3, so 1,000-fold, 100,000-fold, relative to benzene. The alkoxy and hydroxy ones are about 1,000-fold. Why is this one not quite as good as that? It's because oxygen is more electronegative than nitrogen. So there's superimposed a relative inductive effect. Oxygen pulls more than nitrogen inductively, so overall, even though resonance wins, the activation power is best for nitrogen. Okay? And then oxygen. Then we have weak activators, and that's alkyl. And notice alkyl is really, a pussy compared with these two guys. It's only a factor of 10. Okay? Small. 10 is not bad, though, for synthetic purposes. If you have a 10 to 1 relative rate between two competing reagents, that gives you, 90% yield of what you want, and that's perfectly fine. Okay? But it's not big compared to, to 100,000. Phenyl is also an activator, and the reason it's an activator is because you can delocalize plus charge into the substituent phenyl. Okay? So picture two phenyls attached to each other, it's called biphenyl, and you do electrophilic aromatic substitution on one. It's a weak activator. Ortho-para is good because the plus charge next on the carbon that's substituted by the second phenyl, you can delocalize the positive charge into that ring. And so that's good. Okay? But it's not big. Then there are the weak deactivators, and these are the halogens. And remember, they're weak deactivators because the inductive effect basically slightly overrides the resonance effect. And notice again, it's not big. Okay? I'm giving you 10 to the -2. This is sort of averaged out over all of them. Fluorine is the worst camper, but chlorine, bromine, and iodide is more in the order of 20, 30-fold, slowing down. Okay? So that's also not big. It's sort of comparable to the weak activation on the left. These two guys are they're softies. Okay? The strong deactivators, on the other hand, really slow things down. And notice here, the carbonyl is the first one, but you have much stronger deactivation if we go to nitriles. Surprisingly, trifluoromethyl, which is only inductive. The fluorines are such strong polars that the inductive effect is stronger of trifluoromethyl than the resonance deactivation of carbonyl. Kind of interesting. But the big winners are these guys over here. Sulfonic acid, nitro is a big deactivator. And ammonium, of course, because it's got a full positive charge. And so what you go from 10 to the -5 to 10 to the -8. So that's, with nitro, you go down to 100 million-fold retardation, slowing down the electrophilic substitution. And if you look at the total range spans 13 orders of magnitude of relative reactivity. But if you translate this into kcal, it's all perfectly accessible within the comfortable regime of temperature for synthetic cook, where you can go up to 150 or so degrees to overcome relatively high activation energies, meaning low rates, slow reactions. Okay. So much for monosubstitution. Activators, ortho-para, deactivators, meta. That's the take-home lesson so far. Okay. So what happens when you have two substituents? And now the game gets a little interesting, right? Particularly when the two substituents are different, because now you're desymmetrizing the system completely. And so in principle, for an ortho-disubstituted system, you have 4 different products that could be formed. For a meta, also 4 different products. For a para, because of symmetry, there's a mirror plane through the molecule, only 2. So that helps. So it very much depends on whether the substituents are the same or they're different, and where they sit with respect to how many options you have. But regardless of all the options that you have, is the picture really as bad as it seems to be, or do we get actually quite a bit of selectivity? And there's some simple rules for this that simplify the issue quite a bit. And the bottom line really is, and that's intuitively totally reasonable, the activators on the ring control what happens. And that makes sense. Activators accelerate. Okay? So they control where things are going to go. The deactivators don't get into the pictures because they slow things down, and they're just ignored because the activators win out. Okay? So what do I mean by that in general? Well, the most powerful activator, so there are guidelines here. The most powerful activator controls the position of attack. So if you have hydroxy versus methyl, strong activator, weak activator, it goes ortho to hydroxy. Para is blocked, so that solves that problem. No product mixtures, only one product. Methyl versus nitro, methyl wins. That's a weak activator, strong deactivator. Only one compound, ortho. Carboxy versus amino, strong deactivator, next to a strong activator, obviously the activator wins. And now we have ortho-para, okay? So we can't get around that, with the exception that there's slightly less ortho than para because of sterics. Okay? So you can say synthetically this is a useful reaction to assume it's going to go para. And here we have methoxy versus bromine, strong activator, weak deactivator, obviously methoxy wins, and we have ortho-para. And here, because it's completely desymmetrized, in principle, you would get 3 different compounds. Well, for steric reasons, as we'll see more of in a second, this position, which is ortho to 2 substituents, is much more sterically hindered than just one substituent. So that really retards attack at this position here. So if you're flanked by 2 substituents and you're competing with positions that are flanked by only one substituent, you lose. So you can cut this off, and so really it's only ortho-para that is to be considered. And here we can't play the game of para being in preference to ortho, because para usually is away from the substituent, because this para is actually next to the other substituent. So here that ortho and para sterically are comparable. You got a mixture. So here's the generalization of guideline 1 into classes. With 3 classes of substituents, the strong activators, basically nitrogen and oxygen. Okay? Then we have the medium guys that are either weak activators or weak deactivators, and that includes the halogens and the alkyl groups. So that's class 2. And then we have the last class that are the strong deactivators. So the first two are all autopara directors, whereas the last one is clearly meta director. So if there is competition for regioselectivity between members of the same group, then you have to hand wave. Okay? Because in principle, that should give you a mixture. So you have to look for steric effects or some other effects that might give you selectivity. So in this case, it's straightforward because it's symmetrical. So dibromo, you get ortho, well, this is ortho-para directing, but para is blocked, and this guy is para is blocked too. And ortho, all the orthos are the same. Okay? So because of symmetry, only one compound, no competition. But here we have a case where there are two activators and they're different, slightly different, two alkyls. And there you expect a mixture, because going ortho here, that's when methyl controls, is about the same as going ortho here, that's when ethyl controls. Okay? So you can't get around that. But if you turn one of these guys into isopropyl, that's branched, much more bulky, the ultimate one would be tertiary-butyl, then indeed we'll get much less of this ortho, and with T-butyl exclusively ortho to methyl. Okay? So you have to look at the fine structure, the finer details to determine this. All right, so we now look at two methoxys. And in principle, you could say, well, okay, they compete because this methoxy goes orthopara here, and this methoxy goes orthopara here. But by symmetry, these positions are related. And what it basically means is that you get two compounds. Because this guy will put the it will go ortho, and this guy will enforce the para. Okay? So you get a mixture. With the argument that you could say you get more of this guy because this position here is less hindered than that. Okay? And you will. 20-80, 30-70, that kind of ratio that we've seen. Okay? So in that, you can live with. As long as you want the dominant product. Synthetically, that's an acceptable choice. If you want the minor product, that's not acceptable because 20% is a really bad step in a total synthesis. And we'll see ways to solve this problem. So here we are competing. The carboxy competes with nitro. The carboxy will be meta directing. This meta is blocked, but this meta is open. It'll direct here. The nitro group will compete with carboxy. We also be meta directing. This meta is blocked, and this meta is the same as carboxy. So here both of them actually push in the same direction. So no conflict. But when you put two carboxys or two strong deactivators, resonance deactivators next to each other, again, one of them, well, they both direct meta. This guy will direct meta here, and this guy will direct meta here. So the same as over here, where it's activating. Here it's deactivating. And you get a mixture with the exception that going here, which is next to the carboxy, will be less compound than going to the unhindered position. So that's good. So when you have a situation, and this is just that we already in a way did this, where there is a real conflict, sterics become quite important. And so here's the case where methyl is juxtaposed T-butyl. So you should really get attack at both of these positions because they're both ortho to the activators. This one is sterically bad, and so to indicate that, I use a dashed line. Here we have a similar situation. Methyl is a weak activator. This is a weak deactivator. You ignore the deactivator. Methyl controls. But that means that it will go ortho-para. There's one ortho, second ortho. Here's para. 3 products possible. This one you can discount because it's coming into a position that's flanked by 2 substituents, much more hindered. That's out. But the other 2 are reasonable. Okay? So you'll get a mixture, but of only 2 compounds instead of 3. Over here, we got 2 alkoxys. They're both activating. This methoxy directs orthopara here, here, and here. And this methoxy directs orthopara here, here, and here. They both work together. So 3 products in principle. But this guy is ruled out because it's between the 2 substituents. So only 2 products to worry about. Sulfonic acid, similar thing. This one directs meta. This one directs meta. They compete, but attack next to the sulfonic acid is slowed down. So we get primarily attack here. And there's a sort of picture that gives you a little bit of the space-filling picture of these substituents. T-butyl is really massive. Right? It really boxes in this hydrogen here. And coming in from the top onto the benzene ring is really impeded by the T-butyl. Much better go here. And here, these 2 substituents gang up to make this position, also this carbon here specifically, much more encumbered than these 2 carbons here. And same thing here, methoxy and ethoxy. Sulfonic acid is quite bad also. It's a big group. It actually gets worse in solution because if you use some hydrogen bonding solvent, then the solvation shell will be even larger. So this group is rather big, so ortho to sulfonyl is not so good. It likes to be further away. And guideline 4 is really just taking it further. And you might say, oh, no, not more. Now we can look at 3 substituents. Will it get even more complicated? And the answer is no. Because what happens, something you may not have noticed, or maybe you have, the more substituents you have on a benzene ring, the fewer positions you have open to attack. So the problem actually gets simpler. And all the rules still, guidelines 1 through 3 still hold. So always the strongest activator is a control, and steric effects on top of it. Okay? So let's look at this 1, 2, 4 substituted system. 2 weak activators, a strong activator, amino wins. Ignore the rest of them. Okay? So you focus go straight beeline to the strongest activator. Everything else is ignored. And that really makes this whole game very simple. And so because of the degree of substitution, you notice that you have ortho-para. Para is blocked, but you still have the 2 ortho positions, but this one is sterically much more hindered than that. So you only get 1 product. Here we have weak activator, 2 strong deactivators, also 1, 2, 4. Ignore the blue guys, the weak activator wins, and it's orthopara. And notice what happens here, again, because of the substitution, there's only 1 position left to go for. So this is totally selective. Okay? No big deal here. This one's blocked, so only 1 compound. And now if you put in 4, notice 4, that means that 4 positions are blocked. There are only 2 positions left. So now there's really only just a 50-50 chance of getting it right or getting it wrong. But again, the strongest activator wins, and that is clearly amino. And both of the others are deactivating. So amino is orthopara directing, the 2 orthos are blocked, only 1 compound, para to amino. And finally, have 3 of the same alkyls, okay, 1, 2, 4 substitution. They are all ortho-para directing, so this T-butyl would direct here, the para is blocked, and this ortho is blocked. The methyl would direct here, that's blocked, here, and here. And this methyl is similar, it would direct here, here, and this is blocked. So it only goes here because T-butyl blocks its ortho position, and the two metals block this position that is flanked by the two metals. And so it only gives you one compound, and that is attack at that position there. So while at first it looks like this could be a very complicated scenario, it's actually quite simple. It boils down to very simple rules. Donors, orthopara, acceptors, meta, superimposed are the steric effects, and the strongest activator controls where things go. So let's leave it at that. I'll see you on Thursday.